Welcome back to Reciprocal Functions Part 2. Based on analyzing the table and graphing y equals cosecant x, can you graph a period of y equals secant x? Hopefully you remember from the last video that we started with the general sketch of sine. So in this video we're going to start with the general sketch of cosine. And we know the general shape of a cosine function is something sort of like this, where the maximum starts at 1, it goes down to a minimum at -1, and then it comes back up to 1 at 2 pi. And so I'm going to draw vertical asymptotes wherever this cosine function crosses the x-axis, because that is, in the reciprocal function, that's where we will have values that are undefined. And now I just draw the pieces of my secant function. Remember, they bump each other. They're reciprocal with the given trig function. They bump each other at the maxes and mins. And then they hug the asymptotes either to positive or negative infinity. So there's a basic sketch of the secant function. So can we state the domain and range now? Well, the domain is going to be all real numbers except for multiples of pi over 2. So we can say x is all real numbers, but x cannot equal n pi divided by 2, where n is an integer. And I'm going to give you new notation here. This z means this like fancy z. That's an integer. That represents an integer. You can look it up. So that's plus or minus 1, plus or minus 2, plus or minus 3, etc. So if you define your multiples of pi over 2, both on the left side of 0 and the right side of 0, to be multiples of the integers, you'd have to multiply pi over 2 times either plus or minus 1, plus or minus 2, plus or minus 3, etc. The range for the secant function would be anything from 1 or higher and anything below or equal to -1. So we can write our range as -infinity to -1, union 1 to infinity. So let's look at graphing the cosecant and secant functions. We're not just going to stop at a fancy little sine and then comparing it with the reciprocal. We also have to look at the transformations that will occur with those reciprocal functions. And so the graph for y equals a cosecant k times x minus b, or y equals a secant k times the quantity x minus b with k greater than 0, we'll need to do the following. First, graph the corresponding reciprocal functions as a guide using a dashed curve, like I just did in the previous example. That is, to graph a cosecant with scalars, etc., we'll use the same scalars. Everything is the same except we change out the reciprocal function for the original sine function. So instead of cosecant, we graph sine, with everything else the same. Similarly, with a secant, we graph everything but swap out secant with cosine, and then we'll be able to use that as a guide. We'll sketch the vertical asymptotes first. They will have equations of the form x equals c, where c is just an x-intercept of the graph of the guide function. Note that the period for these functions is 2 pi over k. That's on purpose, so this goes a little faster. So if k is factored out, then it helps us very quickly determine what our number of periods will be and the length the periods will be. Sketch the graph of the desired function by drawing the typical U-shaped branches between the adjacent asymptotes. The branches will be above the graph of the guide function when the graph of the guide function values are positive, and below the graph of the guide function when the guide function values are negative. So those are the big takeaways from this page. So to practice this idea of graphing these reciprocal functions, let's go ahead and graph one period of y equals 3 cosecant of 2x, and then we'll need to state the domain, range, amplitude, period, and phase shift. So first, we look for the reciprocal function, which is a cosecant. That means that we're going to graph a guide function as 3 sine of 2x. Remember, if there's a scalar out front, we know that we can take 2 pi, divide it by k, which in this case is 2, and we get the length of the period. So the period is pi in length. So if our graph is showing 2 pi, we would have 2 periods of the cosecant in that length on the x-axis. Well, the next thing we have to figure out is how tall we should keep track of. We have an amplitude of 3 here. There is no vertical shift up or down, and so now I can just graph the sine function to determine what to do with the cosine or the cosecant function. My sine function will start at 0, 0, go through pi over 4, pi over 2, 3 pi over 4, and then back to pi. So I'm going to go ahead and draw this as a dotted line. And so now I can use this as my guide. Now I'm going to identify the x-intercepts, which are at 0, pi over 2, and pi. And I'm going to draw in my vertical asymptotes at these points. And now I can actually use that to graph the cosecant. So I'm going to fill in the maxes and mins because those bump each other. And then since this first interval from 0 to pi over 2, the dotted graph is above the x-axis, that means my u is going to be opening toward positive infinity in the y direction. And from pi over 2 to pi, I know my graph is below the x-axis, which means my u shape will be opening downwards and tending toward negative infinity in the y direction. This is one period with amplitude 3. We'll say the period is 0 to pi. So it's an interval from 0 to pi, or we can just say it's 2 pi divided by k, which equals pi. I would take either answer, but each instructor is a little different. And the phase shift would be as if this had been added to or subtracted from on the inside of the sine function, and that didn't happen, so there's no phase shift. Now we need to state the domain. The domain for this function is anything except for x cannot equal 0, pi over 2, pi, etc. So pi over 2 times n, where n is an integer. You're going to have to get used to seeing this because this says that for any multiples of pi over 2, there's a vertical asymptote. Now let's look at the range. The range is how far up or down I go. And in this case, anything 3 or more, or anything -3 or less is part of the range. So we can say our range is from -infinity to -3, bracket, union bracket 3 to infinity. The next exercise is y equals -1/2 secant of 3 times the quantity x minus pi over 6. We need to identify the period, which we can do by taking 2 pi and dividing it by k, and in this case that's 2 pi divided by 3. We need our phase shift, which in this case is how far it's been either added or subtracted from x. So since it's subtracting pi over 6 from x, we shift it to the right by pi over 6. And our amplitude is the absolute value of a equals 1/2. And it is a reflected graph about x-axis. I think that pretty much covers it. We now need to replace secant with cosine. So instead of y equals -1/2 secant of stuff, we'll have y equals -1/2 cosine of this stuff. 3 times the quantity x minus pi over 6. And at this point, if you're feeling a little overwhelmed by the amount of stuff that you have to keep track of, I think I should just, full disclosure say, yeah, there's a lot. And I feel sometimes like there's a lot to keep track of here with the transformations, which is why I love those tripartite inequalities so much. Because I know that a cosine period is from 0 to 2 pi. That's so comfortable after all this new transformation stuff. I just put that inside of the function cosine into this inequality. And then I solve for x. My goal is to get x all by itself. So the first thing I'm going to do is multiply everything by 1/3 to get the 3 out of there. Now I have 0 is less than or equal to x minus pi over 6, less than or equal to 2 pi over 3. Next, I'm going to add pi over 6 to all 3 pieces, which means I'm also going to need to multiply my 2 pi over 3 by 2/2 just to get a common denominator. So pi over 6 is less than or equal to x is less than or equal to 4 pi over 6 plus 1 pi over 6 is 5 pi over 6. That tells me where to start and stop on my x-axis. So I'm just going to break this up into pi over 6's. So pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, and clearly these will reduce, 6 pi over 6. So that's pi. And so I now have everything I need. I know that my period for this secant function exists between pi over 6 and 5 pi over 6. I've gone ahead and reduced my fractions in the pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, and pi. And now I'm going to draw the interval in highlighter where this function exists, from pi over 6 to 5 pi over 6. Now I'm going to sketch the negative cosine of it, which will go from a low number, a minimum, through pi over 3 to a maximum at pi over 2 of 1/2, and then it's going to go down again, cross at 2 pi over 3, and get to a minimum at 5 pi over 6. Now, because of that, I can identify where my vertical asymptotes will be on the reciprocal function, which is at pi over 3 and 2 pi over 3. I use that to sketch my reciprocal function. I know that they bump at the maxes and mins, and they tend toward the asymptotes as they approach positive and negative infinity. So I have something like this. Secant approaches negative infinity as it approaches pi over 3 from the left, and it approaches positive infinity as the function approaches pi over 3 from the right. And so you can see how whether the function is positive or negative can determine whether the u goes downward or upward as it tends toward positive or negative infinity. Since this is negative from pi over 6 to pi over 3, positive from pi over 3 to 2 pi over 3, and negative from 2 pi over 3 to 5 pi over 3, you can see how these u-shapes tend toward the direction of the sign. The domain for this function is all real numbers except for x cannot equal pi over 3, 2 pi over 3, and you can see how this would continue on 3 pi over 3. So it's multiples of pi over 3. And so I can write this as x cannot equal n pi over 3, where n is an element of the integers. And the range is negative infinity to negative 1/2 union 1/2 to infinity. And notice I put brackets on the 1/2 and negative 1/2 because we include those max and mins.